Hello there, ladies and gentlemen, and welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los. Let's get right to it. We're going to talk about oxidation and reduction today. So you know how we do here. Grab your popcorn, get ready, get excited, tell your friends, tell your friends and family. This is going to be good. So this stuff we're going to talk about today, it can be a little confusing from time to time. The terminology especially is confusing. Sometimes I almost imagine, like whatever scientists, I don't know who gets to come up with this stuff, but, doing one of those little, maniacal type laughs as they come up with this terminology, and imagine all the students in the future that are going to have to actually learn this stuff. But, it's not that bad. We'll get right down to it. So, oxidation and reduction. Many chemical reactions, most in fact, involve the exchange of electrons. These are known as redox reactions, which stands for reduction oxidation. And so what we need to define is define oxidation and reduction. So losing electrons is known as oxidation, and gaining electrons is known as reduction. And, right there, right off the bat, we can be a little bit confused about that, like why gaining electrons would be called reduction. This is definitely very important, something to remember. I don't know why for sure that it's called reduction. It does get reduced, and a species will get reduced in charge when it gains an electron, so that is possibly where it comes from. But one little trick or mnemonic to remember that is Leo the lion goes grr. Leo the lion goes grr, and that stands for losing electrons is oxidation, gaining electrons is reduction. So when something gains electrons, we say it has been reduced. When something loses electrons, we say it has been oxidized. Not that you necessarily need to write this down, but actually the majority of chemical reactions are redox reactions. We've already been talking about some redox reactions. We just haven't really used that term. The major examples of things that aren't are double replacement reactions and acid-base neutralization reactions. Aside from that, really, nearly all of the chemical reactions you look at end up being redox reactions. So a little bit later in the course, when we study organic chemistry, redox always means the same thing, but this is just something that I'd like you to take it down in your notes now, and something we might remind ourselves of later. When we study redox in organic chemistry, it's going to be more useful to think of it in a different way, or sort of think of it as defined in a different way. Again, in the end, it all means the same thing, but when you're looking at organic compounds, by the way, organic chemistry is a study of carbon. If you didn't know that, carbon does some very complex chemistry. So when we come back around and look at this again in organic chemistry, it might be useful to think of oxidation as the gain of oxygen or a loss of hydrogen, either one. So that makes sense, oxidation gaining oxygen, and that's actually kind of where some of this originated. And then reduction means loss of oxygen or gain of hydrogen. And again, this does not work in every context. This is going to be most useful when we're studying organic chemistry. Oxygen certainly isn't going to be, it's not always going to be involved at all, nor is hydrogen. But something to keep in the back of your brain for when we do the organic. So, oxidation numbers. Oxidation numbers are a way of keeping track of electrons. You can sort of think of it as the charge of an atom or ion. And if you have a redox reaction, oxidation numbers are going to change for at least some of the elements or species involved in the elements involved in the redox reaction. There'll always be a pair that will change their oxidation number before the reaction versus after. And like I said, they're kind of a way to keep track of electron changes. They're a way to keep track of where electrons are going. And your workbook has a whole list of oxidation numbers. I'm going to show them to you on the next couple of slides. I don't think there's necessarily any reason to write them down in your notes unless you want them in there. It's a little bit wordy, but there is a copy of it in your workbook. I'm going to go through these rules very quickly right now, and we're definitely going to spend some time in class really working on assigning oxidation numbers to things. But just quickly brazing through some of these rules here, I can't stress the importance enough that if you have an element in its elemental state, its oxidation number is 0. It has no charge. It's a big misconception that pops up. I'm always saying column 1 of the periodic table, which is where sodium is, that's the +1 column. That's true, Sodium forms +1 ions when it undergoes a chemical reaction and forms an ionic compound. But if you just have the element sodium sitting there, or copper, or oxygen, or any other element, it has no charge at all at that point. So very, very important. And there's a gigantic difference between uncharged elemental sodium and Na+1. Elemental sodium will explode when you put it in water. Na+, totally harmless, safe, and you need it, in fact, for body functioning. So this stuff will kill you. This stuff you need. So very, very dramatic change happens when this thing attains a charge. So yeah, if we're asked, what is the oxidation number of any element in its elemental state, not part of a compound, it's 0. If we're asked what is the oxidation number of a compound, oxidation state, oxidation number, by the way, kind of interchangeable terms, but if I just say what's the oxidation number of this thing right here that I'm circling, well, it's +1. The oxidation number of this is -2. By the way, note that when we write the charge here, we can put the minus in the back, but IB is very particular about if you're asked what is the oxidation number of this thing right here, putting the minus charge first. You literally will get it subtracted if you wrote down 2 minus. So I don't know, weird IB thing. As far as ionic compounds, we should be used to this. Again, we can just look at it like the charge. So here we have in a compound, the Na is +1, -1. Here the oxygen is -2. And then there are 2 coppers, which are a total of +2. But the question is, what is the charge on each individual copper? Each one of these coppers must have a charge of +1, because the charge is 0 on the thing overall. Here, again, oxygen has a charge of -2. Well, this copper must have a charge of +2 to balance out that charge. Again, same stuff that we were looking at when we were writing Roman numerals, when we wrote, this is called copper 1 oxide. Without you realizing it, that Roman numeral 1 is the oxidation number of the copper. So you were figuring out oxidation numbers without realizing it when you were writing formula names with Roman numerals in them. The sum of the oxidation states of a compound is 0, and in a polyatomic ion, the sum is going to be the total charge. So again, we know the net charge here is 0, so if chlorine is -1, sodium is +1, etc. And again, we're going to this fast. We'll do more examples in class. What's going to be a little bit new is in covalent compounds. What are we going to do about that? So the big rule there is we're going to give oxygen. We're always going to give oxygen a -2 oxidation. Well, almost always give oxygen a -2. And then we're going to kind of figure out other things from there based upon giving oxygen a -2. So for example, in O2 here, if the oxygen is -2, well, then the nitrogen would have to be +4 because we know they have to sum to 0. In the case of the carbon, or the CH4 here, methane, we're going to give the hydrogen a +1. That's total +4, therefore the carbon is -4 here. This, which I guess technically is an ionic compound, but a little different than what we're used to. In this case, because this is an ionic compound, so I guess it's a little bit different than these other ones, I'm going to give the calcium the +2. Basically, calcium's oxidation state, if it's not 0, if it's not the element, it's always going to be +2. It's in that +2 column. So therefore, the hydrogens here, in this case, might be a -1. So that's basically what that last line is talking about. Now, what if we had something like IF4? What kind of charges would you assign to that? Well, we would decide about the electronegativity of each element. Perhaps you recall the electronegativity trend is that electronegativity increases going towards fluorine. So going up and to the left, electronegativity, or to the right rather, electronegativity increases, not counting the noble gases. So in these kind of covalent substances that don't have hydrogen or oxygen, the more electronegative element is assigned its a typical negative charge. So fluorine is in the -1 column. So I would give fluorine a -1. Therefore, a total of -4 from the 4 fluorines. And then the iodine would have to be +4. Now this last one, this is not going to come up too often, maybe every now and again. Notice O2 -2. So 2 oxygens with a -2 charge. That's a type of ion called a peroxide, as in hydrogen peroxide. And if you think about it, if it's -2, each one of the oxygens must be -1. If this little O2 dude has a total of -2 in charge, each one of the oxygens must be -1. So that's the one time where we're going to give oxygen a -1 oxidation state. Okay, and again, we're going to practice more with that. Super key to get that locked in before we really master some of this other stuff. So let's look at another term here, another one of these wonderfully confusing terms. In a chemical reaction, matter cannot be created or destroyed, so if one species, if one thing is gaining electrons, something else has to be losing it. So the thing that gets reduced, it has to get those electrons from somewhere. You know, they can't just come into thin air. So there are these things that we call reducing agents. Reducing agents cause something else to get reduced. Reducing agents lose electrons and therefore themselves are getting oxidized. And then oxidizing agents cause something else to get oxidized. So oxidizing agents gain forward electrons and themselves are getting reduced. Clear as a bell, right? Yeah, it is a little confusing, but basically, reducing agents get oxidized, oxidizing agents get reduced. When it says reducing agent, it means it is the thing in a chemical reaction that's helping to reduce something else. So if it's going to reduce something else, in other words, it's going to give electrons to something else, it is losing electrons and getting oxidized. Oxidizing agents are the things that are sort of taking the electrons, they themselves are getting reduced, they're helping something else get oxidized. You know, I didn't invent this terminology, but it is what it is, and we're just going to have to try to get used to it. Perhaps you hear my son down there. He seems to be enjoying himself. So let's just look at this in the context of an actual chemical reaction. So here we would have called this a synthesis reaction here. We have the element sodium reacting with the element chlorine and making sodium chloride. So let's think about what the oxidation numbers are here for everything. In the case of sodium, it's 0 because it's an element in its elemental state, as it is with chlorine. So here we have a normal ionic compound where sodium is +1 and chlorine is -1. So remember, if we're thinking about a chemical reaction, this is like the before and this is like the after. Yeah, so here we have the situation. These are both 0. These are +1, -1. And let's kind of think of what happens in terms of the before and after. So sodium, the element sodium here, is getting oxidized. Its oxidation number goes from 0 to -1. So it has lost an electron. Leo the lion goes skur. Losing electrons is oxidation. Gaining electrons is reduction. So sodium has gone from 0 to +1. That means it has been oxidized. Chlorine, on the other hand, the element chlorine here is getting reduced. It is gaining electrons. So chlorine's oxidation number is going from 0 to -1. So it means it has been reduced. So on the other hand, sodium is the reducing agent. So the reducing agent, remember, gets oxidized. So sodium is the reducing agent. It is giving electrons to chlorine. It's helping chlorine to get reduced. It is the, the agent, a sports agent or whatever, who works with an athlete. He's helping the athlete get a contract. In this case, sodium is helping the chlorine get reduced. So it's the reducing agent. It's giving electrons to chlorine, so it's getting oxidized. And then chlorine is the oxidizing agent because it's the thing that's taking electrons. So sodium is oxidized. Therefore, it's the reducing agent. Chlorine is getting reduced. Therefore, it's the oxidizing agent. And there you have it. Like I said, piece of cake, right? We'll talk again. We'll continue to talk and practice with this, and it's not so bad once you get used to it. Another thing that's pretty critical to a bunch of this thing is called half reactions. There's a bunch of different contexts where we might want to split a full reaction to half reactions. Half reactions isolate either the oxidation half of the reaction or the reduction half of the reaction. And again, the actual context when we use this will come down the line a little bit, but it is critical to be able to write half reactions for good reason that we'll see. What I can't stress enough is half reactions themselves are not complete chemical reactions and cannot happen by themselves. They need the other half of the reaction. So we're taking an actual complete chemical reaction, we're splitting into its parts, neither one of which could happen on its own. So just like all reactions, half reactions have to be balanced for atoms and charge. The charge has to be the same on both sides of the arrows, not necessarily 0, but the same. And then we use E- symbols to represent electrons, and those are going to balance charge. So we're going to talk a ton about this in class, but just a quick example so you can have one in your notes, and then you can have that when you want to go back and look at it. Take this top reaction here. So I've written a net ionic equation, which is another thing if we haven't yet, we might want to remind ourselves about how to do, but let's just take it as it is for right now. So notice we have zinc going from Zn to Zn2+, and we have Ag2 plus going to Ag. So we could think for a second about what has been oxidized and what has been reduced there. But as we can see, the oxidation half reaction here, as a hint, the zinc is going from Zn to Zn2 plus, so it has been oxidized. So notice I'm showing the oxidation part of the reaction here all by itself. So the zinc is going to Zn2 plus, and there's 2 electrons to balance the charge. Notice that the charge is 0 on both sides of the arrow here. It won't always be 0 necessarily, but it does have to be the same. This is an element in its elemental state, so its charge is 0. This thing has a +2, but there's 2 electrons that total -2, so the net charge is 0 on both sides. The reduction half reaction, what is getting reduced is these Ag plus ions, not the element silver. Ag plus ions are the things that are getting reduced, and 2 of them. So 2 Ag plus ions are gaining an electron apiece, so a total of 2 electrons, forming elemental silver with no charge. So the reduction half reaction is 2 Ag plus 2E minus and 2 Ag. And again, net charge is 0 on both sides here. +2 cancels out with 2 electrons going to the uncharged silver. And that, I think, is it, ladies and gentlemen. Thank you very much for listening. We'll talk more about this next class. We'll go on from there, try to get all this weird stuff hammered out. But thanks for watching. Have a good day, and we'll see you next time.